Thanks for having me here. So I'm Jiajing from MIT, and I'm going to talk about learning physical interactions in many ways. So it's about how we can learn the interactions for rigid objects, but also even non-rigid objects, how to predict how they will move with the help of our physical knowledge. So it'll be more like how physics or science can be used in machine learning or AI, rather than how machine learning can be used for science. But hopefully some of the messages I deliver can be also shared. So we humans use a lot of physical knowledge in predicting objects move in our daily life. So here are a few examples in cooking, looking at this person trying to make an egg, or if you want to put butter on the bread, or you're making ramens, or you're making sushis, right? So you have the ability to imagine, okay, what will happen if I perform this particular action? Then by having this knowledge, you can plan your actions accordingly and to really make all those food. And so the objects involved here, so when we are doing all these actions, we're not really explicitly calculating all the physical equations, right? And also for many of these objects, they're rigid bodies, deformable objects, or even fluids. So it's also, sometimes it's hard to really write down the explicit analytical equations for them. So, but we do have some kind of physical intuition about what will happen here. So if we want to build AI models to perform this, how can we really do that? Right? Especially to begin with, what would be the right representations to use in those AI models? So we took inspiration from computer graphics. This is an example from NVIDIA Flex, which is a simulator that NVIDIA built to simulate interactions for rigid bodies, but also fluids and stuff like that. And maybe it's not really the most accurate one, but it does look pretty realistic and plausible to humans. So it's capturing all the intuitions. So what do they use in representing these different scenarios? They use this particle representation, right? So it seems like it's a general, compared with representing every object as a rigid bodies, it seems like this particle representation could be a pretty general representation to capture a range number of objects. So can we actually build AI systems that learns the interactions not within objects, but actually within particles? So how can we do that, right? We propose a method that tries to represent the entire state of the scene as a whole graph, where each particle is a node. And we try to model the particle interactions using graph neural networks. So as a very simple demo, here is a graph where you have a few particles and they have edges modeling their influence with each other. So the graph has objects or relations. And every step, every particle has its own latent properties, which is kind of a learned feature vector for the particle. And then you're capturing what's the effect from one particle to the other by having a graph neural network, taking the two particle representation as an input. And then you can also calculate, okay, what's going to happen to that particular particle in the next step. That is, given its current state, as well as the influence of all the incoming edges, and taking them together through a different neural network, and try to predict, okay, what's going to happen to this particular particle in the next step. And so this is the basic architecture, but then we also need to make a number of architectural changes to make the system work in complex real scenarios. This includes, we need to have multi-step propagation, looking at this example of Newton's cradle, right? If you have the leftmost ball or particle hitting the whole thing, then almost instantly the rightmost particle or ball will move. So you have to really have the multi-step propagation to model the long-range interactions between different particles. And you also need to have this, what we call dynamic interaction graph. Think about if you're representing fluid as a collection of particles, then two particles that are next to each other at this particular time may be pretty far away in the future. So if you're only representing, you have a fixed graph, then it's not going to be able to capture the dynamic changes of the relations or the neighborhoods of each particle. So you have to change your graph or build a graph over time. So that's what we call this dynamic interaction graph. And if you have a large, huge rigid body, think about if you have a huge cube, then if you push it on a particular corner, then the whole cube will move. And even for the if you're representing the cube as a number of particles, then particles that are really far away will also be influenced by particles that are really far away. So you not only need to have multi-step propagation that are across neighboring particles, but you also need this hierarchical structure, right? To have this hierarchical propagation of the effects so that particles that are far away can also have impact over each other. So putting all these together, and by introducing a final architectural design, that is, we have different representations for rigid bodies. Like for rigid bodies, it's a whole thing. So you need this hierarchical modeling, and you're predicting a single global motion for the object. And for default objects, you still have this hierarchical modeling, but you also predict the local motion, so a separate motion for every particle. And for fluid, there's no hierarchy because it's basically homogeneous, and you're predicting local motion for every particle. So putting everything together and applying different techniques for different states, objects in different states, you're able to build an AI system using graph networks and to predict interactions of fluids and rigid bodies, right? So this is what you can do with this learned graph neural networks. And because you're learning everything on the graph, so you're capturing the local interactions, not really the whole picture. So by having this right inductive bias, it allows you to generalize to different scenarios where now you have 2 times more particles than those in training. So you have seen much more. While in training, you're only seeing a half of a particle. But still, the model can generate pretty plausible predictions compared with the ground truth, right? So it does really generalize this. And now having this predictive model, you can use it for control. So there's an example where, because the learned model is a graph neural network, it's naturally differentiable. So you can use the learned model in model predictive control. Basically, if you have the current state and there's a goal. So given a particular policy or action, say U, this is the model tells you, okay, what's going to happen. They can compute the difference between your prediction and the future goal and calculate the difference and then calculate the gradient and think about, okay, how I can just use gradient descent to optimize to search for the policy. So what's the actions I should take? Then I can correct my action to get closer to my goal. So in model predictive control, we assume the model is not perfect, just as neural networks, they're really never perfect. So after predicting, giving you the whole policy, you only execute the first step. Just do one step, and then you get a new state. And then you can do the whole process again, right? You can still use a model to reproduce or repredict what's going to happen, compute a gradient, and optimize your policy. So this is in model predictive control, there you take an action, predicting it, re-optimize the whole action policy, and do it repeatedly. So here are some results, where if you have all those liquid in a box, and your goal here is to shake the box, so that after the countdown goes to 0, so now it's 150, but after it goes to 0, the final configuration of the water matches the goal, which is shown here. Then by having this learned model and applying it with model predictive control, you're able to solve this problem. Right? When it goes to 0, you're able to control the water to match the target configuration as you're shown here. This is a different example where you have this kind of, I would say, plasticine, but we try to play with it to get it into a target configuration after 2 grips. So these are all on synthetic data, but we can also try it on real data. So this is deploying on a real robot where you have this sushi-like particle-based object. And the robot is searching for, using model predictive control, to searching for the right actions to really play with the soft body to match the target configuration as shown on the left. So after 3 grips, you're able to do it pretty well. So here you're using graph networks to learn the interactions between the particles. But then we want to ask the question that is, if you're applying them in these complicated scenarios where you don't really know what's the underlying physical properties, what's the governing physical properties, is that possible for the model to discover them, right? What has the model really learned? So that's a little bit hard to test. So we choose a few simple scenarios where we do know what's the underlying governing physical properties, right? So here the spring scenarios, you have a few particles interacting with each other. There's this charge that's really governing their interactions. And for perfectly elastic balls, the movement is only determined by mass, and inelastic balls where its movement is determined by the mass and coefficient of restitution. So we test our model on these simple scenarios and see what has the model really learned. And we actually find out that physical properties can be decoded from the learned model representation. So we just take the representation learned for each particle by this model and apply a simple PCA, principal component analysis on it, and realize the first and second principal components really align with, has a very strong correlation with the governing underlying physical properties. So in the spring case, the first component is basically aligning with the charge. And in the perfect elastic balls, it's aligning with the mass. And in inelastic balls, the first principal component really align with the mass, and the second component is for coefficient is restitution. It really explains most of the variance we can see in the data. And again, by having this particle or object-based representation, it really generalizes. So the decoding ability, the same classifier you trained to decode mass or friction or these physical properties, you can really generalize to different scenarios. So if you train the model only on 6 objects or 6 particles interacting with each other, but then you have the classifier that can decode physical properties, but now you test it on 3 particles or 9 particles, the classifier is almost able to, or regressor is almost able to do it equally well and also decode physical properties. It can also decode or generalize to values outside the training ranges. So even if the model during training only seeing mass or charge in a particular range, but during testing, you give it different scenarios where the values are outside the training ranges, you're able to decode those properties, not as good as the training values, but pretty well. Okay, so here we're all assuming we have known nothing about physics, and we're just trying to, we know a little bit. We know that, okay, there is kind of a right inductive bias we should put in. That is, objects are mostly homogeneous, so we try to model the local interactions between these particles. And we find out, okay, it can capture these physical interactions, and it can also implicitly learn the physical properties. But there are also many scenarios, as Nancy already said, we already have a physical model for it, right? What if an analytical model is already known? So this is an example where it's a classical stimuli in object interaction, in robot manipulation, that's planar pushing. So you have an object, which is like a pusher, you have the contact location, you have the pusher velocity, you have the object velocity, and you have the center mass. So assuming you know all these properties, then there are all those physical equations that people have developed, I think 27 years ago, that are already able to produce or model these physical interactions pretty well. So what do we do in those cases? If we already have an analytical model, then do we still need machine learning? Well, now I think the answer is not surprising because we can do, I learned this new word, discrepancy modeling. So we realize that analytical models, they're just really never perfect. And if you compare the real motion with the analytical model's prediction, then you realize in the short term, it's doing pretty well, but in the long term, the prediction really deviates from the ground truth, right? Why is that? Again, there's all those frictions, there's the density variations in objects, which are really hard to capture by these models. These models are really making a lot of simplifying assumptions, right? So the real motion deviates from the simulation. That's what we already see in Nathan's talk as well. And a second point I want to make is also the real world dynamics is really stochastic. Even if you have the same initial configuration, where you have the same object and having them interacting in the same way with the same initial configuration, the outcome could be stochastic, right? So dynamics is stochastic, which is also something that analytical model usually don't really capture. So we actually tried to combine learning on top of it. That is, you can take this analytical model, which is known and it's pretty good, pretty accurate, but again, it's making simplifying assumptions, so it's not perfect, it's often deterministic. And you can have a neural network, which is more expressive and stochastic, but often it requires a lot of data to train. So we can learn this hybrid physical model, which is using the network as a correction, as a learning residual, or as a correction on top of the analytical model. So the model not only takes the current state in action, but also takes the analytical model's prediction and learn the correction on top of it. And hopefully it can be expressive, stochastic, and also more data efficient. Right, so it turned out to be the case. So this is an example where we tried on a real robot in planar pushing, where you can see the yellow dots are the ground truth, where there were 2 modes of the possible outcomes. And our model prediction, which is in red, really captures the 2 modes. Well, if you compare with the baseline, which use Gaussian processes, non-neural networks, that only captures a single mode. It's also more data efficient compared with a pure neural network, right? So the red lines are our model's prediction, and if you see, if you want to achieve a 1% relative error in the final position of the objects after pushing, then it requires about 700 data points to achieve the same effect with our hybrid model. And if you compare with a pure neural network, it requires about a little more than 2,000 data points. So it's about 1/3 of the data needed compared with a pure neural network. And again, you can deploy on a real robot. And here the robot tries to perform a highly underactuated task, just like the double pendulum, but this is a different example. Also underactuated on a planar, on the plane. So the robot tries to push the left disc so that it pushes the right disc and reach the target. So with this hybrid physical model, we're able to actually do that. All right, so to summarize, we talked about learning physical interactions using graph networks, and we realized the model can actually implicitly discover the governing physical properties through learning. And we've applied the learned models in rigid as well as non-rigid object manipulation. And we also propose to learn a hybrid model that explicitly incorporates physics. But the key messages here is to think about what physics has already brought us, right? So in fluid or in these kind of scenarios, it's about the object is homogeneous, so you don't have to learn everything. You just learn the local interactions. Really allows you to generalize to more complicated scenarios. And in a hybrid model case, it's about analytical model is just really good, and you already have it. So compared with learning everything from scratch, why don't we just build it in? And then use learning to learn what the model doesn't give us, including those things that are hard to specify, including the complicated scenarios or the frictions or things that we cannot really write into the analytical models, and using learning to learn from data. Hopefully these are the messages that can be useful not only in science for AI, but also in machine learning for science. Thank you very much.